Hello, everyone, and welcome to today's session of InfluxDB IOx Tech Talks. My name is Caitlin Croft. Super excited to see you all here. We'll just give our friends a couple of more minutes to join. So I just want to give everyone a few friendly reminders. This session is being recorded and will be made available on our YouTube channel later today, and the slides will be made available for review. I know a lot of you guys like to review the video as well as the slides later. So don't worry, it'll be available later today. We have lots of different events here at Influx, so we like to stay engaged with our community. So be sure to check out our events page if you're interested in learning more about InfluxDB, or if you're interested in seeing how other community members are using our platform. And of course, we do have these InfluxDB IOx Tech Talks monthly, the second Wednesday of every month. So be sure to come back and hang out with us again in October. Please feel free to post any questions you may have in the Q&A or in the chat. I know we're all pretty familiar with Zoom at this point, but you can find both at the bottom of your screen. We'll take any questions that you may have for the team at the end of this session. So there's a lot of people on today who I know are excited to hear from you guys, understand why you're excited about InfluxDB IOx, and any questions that you may have about the development of it. Want to remind everyone that we have Influx Days North America coming up in October. I can't believe it's next month. It's crazy where this year has gone. It'll be completely virtual. The conference itself is free, and there are a couple of trainings that are a part of the conference as well. So we have our popular Flux training. So if you're relatively new to Flux and you want to learn how to use the new querying and scripting language, be sure to check that out. There is a fee attached to that, and there's also a one-day Telegraph training. So there's lots going on in October. It's pretty exciting. We just recently announced all of our speakers, and the agenda is live for Influx Days. So be sure to check that out. Just want to remind everyone to please be respectful of all attendees and speakers on this webinar. We just want to make sure that everyone has a really great experience. All right, without further ado, once again, hello everyone, and welcome to today's InfluxDB IOx Tech Talks. Super excited to see you all here. My name is Caitlin Croft. We have a bunch of people from the IOx team here, and Raphael will be providing an update. Before we jump into that, I'm totally going to put Paul on the spot and see if he wants to say anything to the community before we jump in.
I don't really have anything to add at this point.
Okay.
We're still doing a bunch of iteration, but as you'll see from Raphael's talk, there's some interesting stuff going in, and there's a lot happening. So.
Perfect. I just wanted to double check, since I know sometimes you like to give an overview. All right, Raphael, over to you.
Right, awesome. So today I'm going to be talking to you guys about observability within InfluxDB IOx, in particular how we use a combination of tracing, metrics, system tables, and some other observability mechanisms in order to debug, to identify issues that are occurring in production and diagnose what might be causing them. Before that, just a bit about me. So I've been a software engineer at InfluxData, working on IOx for about 6 months now, where I've been primarily focused on the data lifecycle, which is how data flows through the system from arriving in a mutable area and slowly getting persisted out to object storage. And then coupled with that, the kind of in-memory catalog representation, which is how that's then coordinated. So there's some kind of locking schemes involved in that. And then finally, I've had a fair bit of involvement in how the gRPC APIs for IOx have taken shape. Now, I've previously worked as a platform infrastructure, SRE, whatever you want to call it, engineer. And so observability is quite close to my heart. I've had my share of getting paged at 2 o'clock in the morning to debug some system. And so I understand the value of a system that's observable and you can actually understand why it's paged you rather than it just paging and going, I'm unhappy. So yeah, I've also been working with Rust for about 2 years now. So this talk, I'd like to kind of answer the how, what, why of observability within IOx. So specifically, what IOx exposes, so the mechanisms, the observability metrics it exposes to the outside world, why these are useful, what you can use them for, what they can tell you about the state of the running system. And then also I'll have a brief section on how this is actually implemented. So the crates, the Rust crates, which are Rust terminology for libraries that we're depending on to provide this functionality. So first of all, the what. Now, one often overlooked aspect of an observability system is how you actually find out what the system's configured to do in the first place. After all, it's quite hard to tell if a system's behaving correctly if you don't know what it's actually configured to be doing in the first place. So the first port of call here is the gRPC management API, which if you've been at previous tech talks, you will have heard a bit more about. But gRPC in and of itself isn't very user-friendly. It's not very easy for kind of ad hoc debugging. So we provide a CLI that can be used to interact with this API. And we can see an example of this usage here. So I'm running a database list command and it produces a JSON output of the databases that are configured. And you can then ask it for more information about the exact configuration of that specific database. In the same vein, we have support for the Google long-running operations API. This will be familiar to anyone who's had any exposure to Google Cloud Platform or any of Google's APIs. They use this extensively. And what this is it's a standardized gRPC service for exposing information about long-running tasks that a system is performing, and it provides functionality for introspecting them and finding out how they performed, what they did, and also provides some functionality for terminating them or waiting for them to complete. So some of the management APIs actually return handles to long-running operations. So then it's up to the caller to decide whether they actually want to wait for that operation to finish. So in this case, you can see that this is a segment of a dump from an operation list command, and it's showing you a compaction job that the system performed in the specific table HTTP API requests total. And we can see it took 844 milliseconds of wall clock time to complete, and it completed successfully, which is always a good thing. On the topic of talking about introspecting system state, it's typical for services to have quite large APIs to expose this information. Fortunately, within IOx, we are relatively spoiled because we already have a fully fledged SQL interface, which gives the full expressivity of the full SQL dialect. So a pattern we're using a lot to expose information about the running system is system tables. And these are tables that look and act like normal, completely normal tables, but which surface data about the internal state of the IOx service you're talking to. So for example, here you can see an example where I start up an interactive SQL prompt. I tell it to use the company census database, and then I'm able to get some information about the data that's been persisted in this case. So I'm listing the system.chunks table, which is a table that contains a record of all of the data that's been persisted and is being persisted. And this gives you some good insights into what the system's doing and what its state is. And we'll see more of this later. And here you can see another slightly more complex query, perhaps, that's making more use of the SQL dialect in order to compute the total amount of data that's been stored in object storage for each of the different tables that have been selected by the predicate. So I hope you can get a sense that this is actually a very useful way to surface information about what IOx is doing and what its state is. We also expose the standard trifecta of metrics, logs, and tracing from within IOx. I imagine these are fairly familiar concepts to most people, so I'll go quite briskly through this, but we expose metrics in the Prometheus exposition format. So this is a HTTP endpoint. You just scrape /metrics, and it gives you this rather substantial text dump of metric information. And typically what you'd then have is running on the node that your workload's on. You'll have some agent that periodically scrapes this endpoint and then takes those metrics and ships them off to some sort of metric aggregator, potentially InfluxDB. And then you'll have some graphing tools or some alerting tools that hang off that in order to provide visualizations and alerting. That's all fairly standard. Logs is also fairly standard. We support outputting logs in JSON, log format, or a non-standard Rust output format that doesn't have a name. So this here is actually log format. Now, one of the cool things about the logging framework we're using is you'll notice these log lines have a level and a target associated with them. And one of the really neat things it can do is you can configure log verbosity at a per target level. So for example, you could configure IOx to, by default, only log warning severity or higher log messages. But then you might say, actually, I want info level logs for just this query module, which is a really useful capability. Currently, it's only configurable at startup, but I would really like to make it that you can configure it at runtime, which the logging framework supports, but we've yet to actually plumb that in. And I think that would give us some really cool capabilities where if you're seeing a log error in a particular module, you'll be able to increase the log verbosity in that module temporarily in order to get better context about that particular error, which I think is really quite cool. And finally, we have distributed tracing. Now, this of the three might be less familiar to people, so I'll just give a little whistle-stop tour of what distributing tracing involves. So let's say we have a user request that looks like this. So you've got a client, they make a request to some ingress service. This ingress service then makes a request to some auth service. Is the user authenticated? If the user is authenticated, the ingress service will then go and make a call to service A, which then might make a request to service B. And the whole goal of distributed tracing is to be able to surface a visualization like this on the right, where you have time advancing horizontally, and you then have a hierarchical rendering of where at each given point in that transaction the time was being spent. So you can see here that it initially spent time calling out to the auth service, and then it spent some time calling out to service A. And you also have some internal data about where within a service it actually spent time. And so the key thing that makes this possible is context propagation. So being able to propagate some information through requests that are made downstream. And this is most commonly HTTP, so including data in subsequent HTTP requests. But a capability I'd really like for IOx is to be able to do that context propagation through Kafka, so through a message broker. And I'll talk a bit about how that's actually a really useful capability to have in a bit. So here is an example of what a distributed trace might look like. Tracing support within IOx is still incubating, shall we say. This is a trace within Jaeger, which is a visualization, a tracing visualizer of an application called Hot Rod, which is just a test application. But I hope it gives you some sense of how you can see the top line, what the user request initiated, and then you can see all of the sub operations that were created and spawned as a result of this request. And so you can get a really good holistic picture of what's involved in performing this user initiated operation, which can be very helpful if it doesn't behave the way that you would like it to behave, or the user would like it to behave. So onto the why. Now I've described what observability IOx provides. Now, observability for observability's sake is a bit pointless. I mean, you can make some pretty graphs, but the real purpose of observability is to detect and diagnose issues. So I'm going to couch this in some case studies that we've already encountered developing IOx. And then some further down the line, I'll describe some kind of aspirational use cases for functionality that doesn't quite exist yet in IOx, but we're in the process of implementing. So the first scenario will be familiar to anyone who's run workloads in Kubernetes, which is that we were seeing IOx pods getting killed for running out of memory. They were getting killed by the C group controller for exceeding their configured memory limit. Now, one of the responsibilities of the data lifecycle is to prevent this happening. It should be freeing stuff from memory as we get close to the memory limit. So if we are seeing IOx pods ooming, that's a bug that should be fixed. And so the investigation of this, you first utilize two key metrics that are produced by IOx at the moment. And these are the chunk usage and the JE-malloc usage. I'm afraid I no longer have the actual graphs. They're outside the retention window of our cluster. So hand-drawn squiggles it is. But this is broadly speaking what it looked like. You had chunk usage, which is the amount of memory that IOx is aware of what it is. And this is the memory usage that the lifecycle acts on. And then above that, you have JE-malloc usage, which is the memory usage that it has actually been allocated from the system. And so you can see here, there's a clear disparity between these two metrics. Something's clearly not right. And so further investigation is warranted. And so the first thing we did was we artificially lowered the memory limit that the data lifecycle would target. So it would basically think it had less memory to play with, and so it would free memory more aggressively. And what ended up happening was it no longer oomed, that the pod was able to reach a steady state. And this was a very interesting data point because it implied that this wasn't a traditional memory leak, because we still had the same ingest load, but the memory usage was no longer growing. So it wasn't a traditional, like we weren't freeing something on the right path. There's also an interesting other aspect to these graphs, which is that as the chunk usage grows up, the rate of memory usage diverges, so that the two lines are divergent when their gradient is non-zero. And this indicates that it suggests that the issue at hand might be down to the chunks not correctly reporting how much memory they were actually using, because as the number of chunks increases, the amount of divergence increases. And this, as it turns out, is exactly what this issue was. Unfortunately, it was quite an undertaking to find exactly where the misattributed, well, the unaccounted memory usage was, but I think we've mostly now gotten to the bottom of it, but hopefully this gives you a sense of how metrics alone can be enough to inform you of an issue and help identify where the issue may be. Now, the next scenario I'm going to call zombie compaction because it amuses me to do so. But effectively, this was an issue that we saw whilst debugging the previous issue, which is that the data lifecycle is supposed to persist data after a certain timeout or a row threshold being exceeded. And for this particular instance, it was configured to be 30 minutes. And so what we would expect to see is that once we stopped writing into this workload, 30 minutes later, all the data would be persisted. Instead, what we saw was 50 minutes of nothing really happening, and then in 2 steps, all the data getting persisted. So something's not quite lining up with our expectations here. So to be clear, these are both metrics that are exported by IOx. So IOx exposes information on where data is within the data lifecycle as gauges, which is very useful for debugging this sort of thing. Unfortunately, it doesn't tell you why the lifecycle is not doing what it's supposed to do. So for this, we need more information. And so we turn to the logs. And perhaps these aren't the most useful of logs. They mean a lot to me because I wrote them. But effectively what this is telling us is that it's trying to persist, but it's unable to because it thinks there's an outstanding persistence operation. So this therefore suggests that either there's a persistence operation that's taking a very, very long time, or it thinks there's a persistence operation and there actually isn't, which would be the worst case. Now, what would normally happen in this case is that if it's delaying persistences, you'd go to the operations API that I showed off earlier, and you'd ask it what jobs were running at this point in time. Unfortunately, in this particular case, I knew that the pod had been restarted, so the server had been restarted, and the operations account isn't persistent at the moment. But fortunately, we have logs, and the operation system will write a log line whenever a job finishes. And so I just went trawling through the logs, and I found this wonder. So for those of you who can't do a nanoseconds to minutes conversion in your head, that's a chunky 45-minute long persistence job. To be clear, these jobs should normally take about 10 seconds. So something's clearly wrong here. I won't go into exactly what was going on here, but suffice it to say, this is not expected, and it helps explain why the observed behavior, which is that once we stopped write, it then decided 5 minutes later to start persisting data, and certain details meant that this was a much larger persistence operation than it would typically perform. And this then effectively stalled the lifecycle out for 45 minutes whilst this crazy persistence job was chugging along. And so this then helps to explain why the lifecycle is not behaving correctly. It's also allowed us to identify a degenerate case for persistence, which needs to be fixed. And it's also highlighted a observability gap, which has since been rectified, which is that we at the time didn't have metrics on how long these background persistence jobs were actually taking. And so that would have really helped debug this issue. And if we encounter it in the future, we'll have a metric that measures exactly the quantity that we're interested in. And it will tell us you have persistence jobs that are taking longer than they should. So this is the kind of iteration process that we follow as we're adding observability to IOx, and also shows how you can use a combination of different observability modalities to build a better picture of what's going on. So one of the other requirements of the persistence story within IOx is it wants to persist Parquet files that don't overlap in timestamps. This just makes the query engine's job easier. But whilst developing the data lifecycle, I wanted to know whether it was actually doing its job correctly. And this is an example of where the system tables and the expressivity of a fully fledged SQL engine become really pertinent, because I can write a query like this, which is able to tell me the degree of overlap between consecutive chunks within a partition. So the cast min value big int nonsense is a current data fusion limitation, which we'll be fixing shortly, to do with arithmetic on duration types. But the rest is fairly standard SQL. So you've got the nested sub-expression is effectively just for each chunk within a partition, it finds the maximum timestamp in the chunk that came before it. And then it computes the difference between the two. And we can see the results of that in this. And so we can see quite happily here that it's producing chunks that have a significant non-negative difference between the min and max timestamp. So these chunks are not overlapping. This is a bit of an idealized case because of the way this metric's collected. But in general, you would see like a couple of hundreds of milliseconds or tens of milliseconds as the delta. And this shows that the lifecycle is actually working correctly. If it's negative, that's a problem. But this is an example of how having that ability to run SQL queries against the state of the system can allow very effective kind of ad hoc investigation into how the system's performing, which I think is a really cool capability to have. Now, the next scenario is a little bit aspirational. This is not currently implemented just yet within IOx. We're well on the way, but we're still getting there. But one of the things we really want to be able to do is we want to be able to render within a distributed trace spans for every single physical operator involved in executing a query. So if you would run like explain analyze on a query, it will report back a large dump of different operators that were involved in the execution and some metrics about how they performed. And we would really like to surface this information in a trace. So it can be surfaced in the context of all the rest of the systems involved in executing a query. So you'll see it propagating through the gateway tier, you'll see it propagating through any other routing or authentication, and then you'll see the actual time it's spent in IOx itself and where within IOx it's actually spending its time. And this gives us two really cool capabilities. The first of these is identification. So one of the things we do in our cloud environments is we routinely capture traces of a percentage of all requests that are made. And what this gets us is it allows us to make assessments from the trace information of 60% of user queries spend 70% or more of their time in the sort preserving merge operator. And this is a very useful piece of information to know, because that then informs that if we can optimize that operator for those workloads, we can lead to a significant performance uplift across a large number of the users of that particular cluster, which is a really useful thing to be able to do. You can work out where the greatest value can be obtained. And also, because of the granularity of the traces, it gives you the ability to analyze at like the per tenant or the per bucket or the per query level and identify behaviors that might not be obvious from the kind of cluster-wide metrics, which are aggregated across all requests. Instead, you can look at individual requests and see where that specific type of request is spending its time, which is particularly useful also for identifying areas to improve. And similarly to this, it helps with diagnosis. So say you've got a query that you know is really slow, you can force a trace of that query, and then you can look within the UI to see where that query is actually spending its time. But also, because we've got this blanket trace capture across all the queries, it can help capture more intermittent behaviors. So for example, 1 in 10 queries, or hopefully not that bad, but like 1 in 1,000 queries fails for some reason, or you've got certain queries that have high tail latency. So sometimes they take much longer than other times. And because we're capturing traces for a large portion of the query workload, we're able to potentially capture some of those extreme cases, which can then help identify what's causing them, whether there's something about the query that's exercising some degenerate case of some algorithm or some hash function or similar. And so it gives you the ability to capture these issues that are otherwise very difficult to get observability into, because they can't easily be reproduced locally. So hopefully that's a bit about why tracing is going to be awesome for query performance once it's fully fleshed out. And similarly, for the ingest path, it's also going to be particularly amazing. So with IOx in a clustered environment, much like our current cloud offering, it's an eventually consistent system. So there's a delay between when a write lands at the routing tier, so when the user makes the request and it's acknowledged, and when that's actually visible to queries hitting the system. And in cloud environments, we call this time to bytes readable. And this is a very important metric to us, and we try to keep it kind of on the order of 100 milliseconds or less. And so IOx is capturing this metric and exporting it to Prometheus. But this metric on its own is not always very actionable, in that it tells you something's wrong. If it's above some threshold, you can see that something's wrong, but it doesn't necessarily indicate what's actually wrong. And so, as I alluded to earlier, a thing I think would be really cool is if we can do trace propagation through Kafka. So the user's write request would appear in a trace, along with it then getting shoved into Kafka, it then getting pulled out of Kafka, and then getting made readable in a query node. And so you'll have this full picture of what is involved in getting a particular write from the ingest all the way through to being able to query it. And so hopefully if you're seeing some issue with the latency of that entire transaction going up, you'll be able to look at the trace and figure out what particular component is behaving anomalously, where the additional latency is coming from. And that's then very helpful for actually actioning this particular alert. So if you're paged because the time to bytes readable has spiked, it's very useful to be able to go somewhere and just get an answer very quickly about where this additional latency has actually come from, because it may be that it's a fairly simple thing to mitigate. So I think that would be a really cool capability that I intend to work on in the near future. So hopefully I've convinced you that there's a large amount of observability that IOx exposes, and we will be continuing to improve upon that as time goes on. But I'll just give a brief whistle-stop tour of how we actually achieve that observability. So for the management API in CLI, we define the API in terms of a standard proto definition. If you've used something like OpenAPI before, it's a similar kind of concept. You define the schema and then you generate code for it. So for Rust, we use prost to generate the protobuf code, and then tonic to generate the gRPC code. Now, one issue we've had, or challenge, let's go with, is that protobuf in and of itself isn't a very user-friendly format. I think most users would consider it a poor experience if your CLI surfaced a base 64 encoded protobuf message. I think they would quite rightfully say that's a pretty terrible, it's a pretty useless thing for it to surface. So there's a need for a more human readable and human editable representation of the protobuf configuration. And so this is actually something that I've very recently written, and we may make available more broadly, which provides an implementation, provides code generation to perform the protobuf to JSON conversion as per the protobuf standard. Because at the moment, there isn't anything within the Rust ecosystem, at least not that I'm aware of, that can do this conversion faithfully. And we would really like to not be maintaining dual schemas for what the user sees and what the API actually consumes. And then for the actual CLI, we're using a thing called clap combined with a thing called struct_opt. So struct_opt's a procedural macro. It just makes it a bit more ergonomic to define CLIs. But if you come from a Golang background, the whole concept's very similar to Viper. Similar. System tables are actually one of the simplest of the observability things to implement, because Data Fusion, which is our query engine, already has an abstraction for plugging in arbitrary data. In fact, this is how we get data into Data Fusion in the first place. So it's fairly easy to just hook up Data Fusion to say, rather than fetching this data from the in-memory catalog, just fetch this data from this synthetic buffer in memory. So that's all very simple. And then the whole query engine magically is able to consume that data and operate on it, which I think is pretty cool. Metrics. So we initially were using a crate called OpenTelemetry. This, we ran into some functionality limitations and some bugs, mainly down to the fact that what we need in IOx is a bit eccentric, in that we need to be able to, so OpenTelemetry is very much designed on the prospect of kind of fire and forget metrics delivery, but we need to be able to actually introspect the metrics we're producing within IOx and use them to act, and the lifecycle needs to be able to act on the metrics that are being collected. And so this created some friction, and in the end we've now settled on using a custom crate to do this, which then has its own in-memory metrics abstraction, which can then be exported to just about anything. We've currently implemented Prometheus export, so it can export the Prometheus metrics that you saw. Logging, we're just using Tokio tracing. There's not a great deal more to say here. We've had some excitement with multi-line log messages and interleaved writes, but nothing that's not unfortunately common with logging frameworks. So some minor pain points, but nothing major. And then distributed tracing. So this is, of course, still very much in the process of being implemented. We initially started using Tokyo tracing. Despite the name, this doesn't actually have a story for distributed tracing. It is very good at tracing, but it doesn't have any story for doing context propagation or extraction. So we now have a custom crate again. This consists of if anyone's familiar with Golang, it's a very similar concept. You can just inject something on the request path that pulls out request headers, munges them in some ways, and then adds an extension to the request context. So that's quite nice. Then that's manually propagated through the rest of the stack and can then be exported to Jaeger, or actually any OpenTelemetry tracing implementation. But Jaeger is the one that we've got hooked up at the moment. And that's it. Thank you.
Awesome. Thank you, Raphael. That was great. So if you guys have any questions for Raphael or anyone else on the InfluxDB IOx team, I encourage you to post your questions, ask them in the chat or the Q&A. I'm always happy to unmute you if you have something that you really wanted to discuss with the team. Raphael, you sort of touched on it a little bit, but why are you excited about InfluxDB IOx?
I'm excited about, well, I'm excited quite a lot about InfluxDB IOx because it solves in a number of previous places I've worked, I've encountered the need for a product very similar to IOx. And I think, especially with regards to cardinality. So cardinality is a really annoying limitation to have to design a metric schema for, because what you really want to be able to do when you're collecting metrics data is collect everything. You want as much granularity and as much information as possible. But because of cardinality limits, you're left kind of juggling what granularity of data can I actually collect. And I think IOx is going to unlock that vector, which would be really, really cool. So yeah, also like most of the tracing systems I've interacted with don't really work very well at large volumes. They have a slight tendency to, perhaps it's just the ones I've interacted with, but IOx, I'm optimistic will handle that case far better than the Elasticsearch that's typical.
Cool. And how can the community get involved? You know, if I'm really excited about InfluxDB IOx, I want to, you know, help you guys out as much as I can, or, you know, just be a part of the community. What can I do?
So we have a public issue tracker for IOx. We also have public issue track that the issue tracker for Data Fusion and Arrow is also public. And it is my belief that Arrow and Data Fusion have this, but IOx definitely has this. Some issues are tagged good first issue. So if you want to get stuck in and start writing some code, that might be a good place to get stuck in, or yeah, or just look through our issue tracker and see what we're currently working on, and feel free to chip in if you have any thoughts about what we're doing, what things you would like to see in that piece of functionality.
Great. Yeah, and I also just want to add that we have the InfluxDB community Slack workspace, and I know you guys are all in there, and there's always lots of questions around InfluxDB IOx, and you guys are always so willing to jump in and answer questions and, you know, listen to the community members' feedback, which I think is great. Cool. Well, we can just keep the lines open here for another minute or two. So if you guys have any more questions, be sure to add them. We're always happy to hear from you guys. And to me, that's the fun thing about open source products. It's seeing, you know, as you're building it in real time, getting that feedback from the users who actually would be benefiting from this product. So I think this is fantastic. All right. Well, thank you everyone for joining today's InfluxDB IOx Tech Talks. Thank you so much, Raphael, for presenting. I think it was a great presentation. Once again, the recording as well as his slides will be made available later today. And we also have the next InfluxDB IOx Tech Talks in October. I believe it's on October 13th. So it'll be right before, kind of uh, leading up to Influx Days. So I'm just going to throw in the Zoom chat, the webinar registrations. So we hope to see you guys next month, and I hope you have a great day.